Okay, Assalamualaikum and have a good day. So this is module 11, parallel algorithm design. Okay, here are the points that I will cover. Okay, I will discuss with you. First, principle of parallel algorithm design. The second, parallel algorithm models. The next one, parallel programming models. The fourth one, Foster parallel algorithm design methodology. And last but not least, some references. And that finish. Yeah. All right. Okay. First, regarding principle of parallel algorithm design. Yeah. What is the core task of this, especially on developing an algorithm? Yeah. Okay, in practice, specifying a non-trivial parallel algorithm may include some or all of the following. For example, first identifying portion of the problem that can be performed concurrently, and next mapping the concurrent pieces of computation onto multi-processes running in parallel. And next, distribute inputs, output, and intermediate data among the processes. And next, managing access to data shared by multiple processes. Next, synchronizing the processor at various stages of the parallel program execution. All right, so parallel algorithm model. So here we got three parts. I will elaborate regarding algorithm model in three parts. The first part, overview of the data parallel model and task graph model. Second one, the part two, detailed breakdown of the work pool model, task pool model. Part three summarizes for the master-slave model and the pipeline model. Okay, part one, overview of the data parallel model and task graph model. When structuring an algorithm, your layout typically follows an established model. Let's look at our first two foundational option. First, data parallel model. In this model, tasks are statically or semi-statically mapped onto individual processes. Crucially, each task performs nearly identical mathematical operation, but execute them on completely distinct partition of the overall data set. Next one, task graph model. Here, the computation within our parallel algorithm are organized as a visual task dependency graph. The structural nodes represent independent operation, and the directed edges represent strict data dependency. This explicit graph is then used to intelligently map workload onto processes or among all the processes that you have. Yeah. Okay, part two, detailed breakdown of the work pool model or task pool model. So our next design option is the work pool, or we call that also task pool model. So this concept or this paradigm is explicitly characterized by a highly dynamic mapping of tasks into active processes to achieve perfect runtime load balancing. Under this framework or design or paradigm, whatever, the same thing, any task waiting in the central pool may potentially be executed by any available process in the system. Because assignment are handled dynamically as processing thread become free. There is absolutely no desired pre-mapping of tasks onto processes before execution begin. Yeah. Okay, part two. Summarize for the master-slave model and pipeline model. To complete our survey, yeah, of algorithm model, let's examine two highly structured workflow model. Yeah, workflow model. Okay, the master-slave model, also frequently called the manager-worker model. So this framework establish a clear hierarchy. One or more dedicated master processor generate computation job and allocate them out to a pool of worker processors, which run them and report back. So the pipeline model, yeah, in this design, a continuous stream of data passes sequentially through a succession of processes. Each process act like specialized factory worker, performing a completely different task on the data stream before passing it forward. This simultaneously execution across a continuous data stream is formally termed stream parallelism. Yeah. So next, regarding parallel programming model, here we got two model that we're going to discuss. First, task and channel model. Second, message passing model. So there are four quadrants or four issues when we talk about the programming model: task channel model, message passing model, data parallelism, and also share memory. We need to manage all this. Yeah. While algorithm models shape our abstract approach, programming model dictate how our code interacts with the physical hardware. The industry groups this into four primary model. Okay, so the task and channel model, next the message passing model, and after that data parallelism, and next one share memory architectures. Let's analyze the property of the task and channel model to see, yeah, how it acts as the foundation for the modern parallel engineering. Okay, all right. So task and channel model. So here are the example that you can see here. Yeah, the diagram will, I mean, I will use this to explain about the concept of this model. Yeah, task and channel model. So regarding that slide, yeah, this is the conceptual layout of the task and channel model. Each circular nodes represent an independent task executing its own code block. Yeah. So these tasks cannot directly read each other local memories. Instead, they are connected by directed channel, which act as dedicated pipes. So data leave, yeah, a task through a green or via a green out port and travel along the channel until it arrives at the pink port on the destination task. Okay, so everything is related to this figure, yeah? All right. So allowing instruction like send message to X yeah, orchestrate the global data flow. Okay, like this example. All right. Okay. So let regarding a component task, yeah. So we need to go each of that, solve the channel. So task, let's formalize the exact technical definition of task under this model. A primitive task is comprised of three distinct elements: a program containing execution instruction, block of local memory, and a collection of input-output I/O ports. Yeah, and the local memory stores the program instruction and local data. For communication, a task transmits its local data outwards to other tasks through its assigned outputs and receive external data into its scope through or via its import. Yeah. So for the component channel, The complementary component in this model is the channel. So we need to have both task and channel. So channel is defined as a message queue that link an output of a sending task directly to an import of receiving task. So channels enforce a strict first in, first out FIFO ordering property. Yeah. So this means that received data always appears at the destination import in the exact same chronological order in which it was placed into the output by the sending task. Yeah. Okay, here is another model, message passing model. Yeah. All right. So in contrast to the fixed channel queue, the message passing model move closer to standard implementation like MPI. Yeah. Here, autonomous tasks forces their own instruction and local data structure, but they communicate by sending explicit messages addressed directly to another target task ID. So a task execute an instruction such as send message to task X, and the underlying network architecture routes that payload directly into the destination task message buffer without needing predefined channel structures. Okay, next, Foster parallel algorithm design methodology. Here, there is flow. So already there is a 4 phases. Yeah, phase 1 partitioning. You need to do this in sequence. Communication for the phase 2, agglomeration phase 3, and phase 4 for mapping. All right. Okay. So now let's dive into the core of Ian Foster structure design methodology as shown in the following slide. This, yeah? All right. So to ensure we design highly efficient parallel software, Foster breaks the engineering life cycle into 4 sequential rigorous phases. First, as we heard just now, partitioning. So here, where we expose concurrency by dividing our problem into primitive blocks. And then for the communication phase, where we map out the necessary information flow between tasks. Then for the agglomeration, where we combine primitive tasks to manage overhead. And for the mapping phase, where we assign our optimized task group into physical processor. All right, here are the diagram or the flow. So there are altogether 4 phases. Yeah, all right. So phase 1 partitioning. Let's examine phase 1 partitioning. This phase is the process of dividing the total computational workload into much smaller atomic pieces called primitive tasks. A highly effective, highly effective partitioning strategy splits both the data structures and the execution computation into as many primitive tasks as possible. Yeah. So the main goal of partitioning is to discover the absolute maximum amount of inherent parallelism possible within the application, the corresponding application. Okay. All right. And then to slice an application, we choose between 2 complementary strategy direction. First, data-centric approach, or we call that also domain decomposition. And the next one, we got computation-centric approach or functional decomposition. For the first one, data-centric or domain decomposition, in this model, we focus on the data first. We divide our massive data arrays or grids into smaller pieces and then determine how to associate computation with those specific data blocks. Yeah. And then for the computation-centric approach or function decomposition, in here, yeah, in here we focus on the operation first. We divide the algorithm execution into distinct functional pieces and then determine how to route data through those individual computations. This approach frequently yields collection of tasks that achieve high concurrency through pipeline parallelism. Okay, now we go for the example regarding domain decomposition. To visualize domain decomposition, look at the data, look at how data can be partitioned across different dimensional plane as shown in figure 1, like this. Yeah, this is a figure 1. Domain decomposition, 1D, 2D, and 3D. Yeah, okay. 1D domain decomposition, we slice a 2D data grid into long, uniform strip, decomposing either strictly in Y direction or strictly in the X direction. And for the 2D domain decomposition, we slice across two X simultaneously. For the 3D volume, this means decomposing in Z and Y, Z and X, or X and Y direction, creating an array of square subblocks. And then for the 3D domain decomposition, we partition across all three spatial dimensions simultaneously, creating a metric of individual data cubes. Slicing data finally generates more primitive tasks, maximizing our architectural flexibility. Yeah. Okay, analogy of decomposition. Yeah. We use the automotive workshop, okay, to represent this decomposition analogy. Okay, you figure 2 represent the 100 car to be fixed and we need 100 car for the output. Input 100, output is also 100. Okay, so this one decomposition, we divided through the functional and so on for the task. Okay, all right. So this is the explanation. Let's use an everyday workshop analogy to understand these two decomposition style. Imagine a workshop, yeah. So this one reflect, yeah, to the figure 1 and figure 3. So imagine a workshop task with repairing 100 broken cars as shown in the figure 2 and figure 3, which is input 100, output also 100, yeah. So we apply the domain decomposition. We split the data, the cars. We assign 50 cars to the team A, 50 cars to another team B, and both teams perform every single repair type. Air conditioning, engine work, and wiring on their own assigned batch of car. If we apply functional decomposition, we split the tasks. So the specialties means team A specialized exclusively in fixing air conditioner. Team B works only on engine, for example. Yeah, this one reflect to the figure 3. Yeah, so team C handles wiring, for example. So the car flow sequentially from one team to the next in the assembly line fashion. All right. So specialized decomposition techniques. Depending on the problem type, we deploy 4 specialized decomposition techniques. As you can see here, first, recursive decomposition used for divide and conquer algorithm. We recursively divide a large problem into independent sub-problems, solve them concurrently, and combine their result. And for the data decomposition, yeah, a two-step method where we partition the underlying data first and use that layout to induce an identical partitioning of parallel tasks performing similar operation. The next one, exploratory decomposition. So this technique, tailor for state space searches. We partition a massive search tree into smaller parts and search them concurrently until the solution is found. Next, speculative decomposition. So this technique is used for conditional branching. While one task computes the actual conditional switch, other tasks concurrently execute all possible subsequent branch paths in advance. And then poster partitioning checklist. Before moving to the phase 2, we must audit our work using poster partitioning checklist. A valid design must pass 4 criteria. So the total number of the primitive task generated must be significantly higher than the number of physical processor in the target computer to ensure flexibility. All right. So you must, you must minimize redundant data storage and redundant computation across tasks. And then for the all primitive tasks must be designed to be roughly uniform in size to maintain balance. The number of primitive tasks must scale up as an increasing function of the overall problem size. So next, phase 2, for communication. Once our computation are divided into tasks, we enter phase 2, communication. Typically, data must be transferred between primitive tasks to allow computation to proceed. This information flow is explicitly defined during this phase. We classify our communication architecture across 4 major categories: local versus global, structured versus unstructured, static versus dynamic, and last one, synchronous versus asynchronous. Okay, communication category explained. Let's define the operational behavior of each communication category. So for the local versus global. So local communication occur when a task only transfer data with a small, tightly bounded set of immediate neighbor tasks. Global communication occur when a task must broadcast or gather data from many other tasks across the network. Structure versus unstructured. Structured communication, forms a clean geometric network like a tree or grid. Unstructured communication form an irregular, arbitrary, arbitrary network graph. For the static versus dynamic, category, so static communication links do not change over time. Dynamic links are determined at runtime by data value and can be highly variable. Synchronous synchronous versus asynchronous. Synchronous data, transfers require the producer and consumer to coordinate tightly in time. Asynchronous transfers allow to a task to pull or push data completely independently without active cooperation from the remote partner. And next, for communication overhead and checklist. Communication between tasks represent pure computational overhead. Therefore, minimizing communication overhead is a critical priority during algorithm design. We contain this overhead by maximizing data locality to minimize both the volume and frequency of data transfer, minimizing resource contention, and strategically replicating small data structure. So according to the Foster communication checklist, a well-designed algorithm ensure that communication operations are balanced evenly among tasks. Each task only talks to a small number of neighbors, and all tasks can perform their communication and computation concurrently. And the phase three, agglomeration. Once our communication is structured, we move to phase three. Okay, phase three, agglomeration. Agglomeration is the process of grouping multiple primitive tasks together into larger. Combine tasks to improve execution performance or simplify development. We do this to achieve three core goals. First, to lower communication overhead by tuning external network transfer into fast internal memory lookups, thereby reducing channel and message counts. Second, to maintain scalability, ensuring all parallel design remain highly effective when deployed onto machine with larger processor count. Third, to reduce software engineering costs by allowing us to reuse existing sequential code structure where appropriate. Foster checklist for agglomeration, for the phase three. To verify your agglomeration strategy, evaluate it against Foster agglomeration checklist. First, check if your grouping has successfully increased the overall data locality of the algorithm. Ensure that any computation you choose to replicate take less time than the network communication they are replacing. Next, verify that the amount of replicated data is small enough to let the algorithm scale up smoothly. And then next, confirm that your newly agglomerated tasks have highly similar computational and communication costs to prevent imbalance. Finally, verify that the total number of tasks remain an increasing function of problem size and is at least as great as the number of physical processor available. All right. So next one, phase 4 mapping. So our fourth and final phase is mapping. Mapping is the explicit process of assigning our agglomerated tasks onto physical processor or network nodes. The mapping phase has two primary competing goals. We want to maximize processor utilization and also at the same time simultaneously minimize inter-processor communication overhead. Processor utilization is defined as the average percentage of time that the system processor are actively executing tasks necessary to solve our problem. We maximize utilization by balancing the computational workload completely evenly. Yeah. So the conflict goal of mapping. Achieving optimal mapping require a delicate balancing act. Inter-process communication decreases significantly when two tasks connected by channel are mapped onto the exact same physical processor because the data transfer happen entirely within local memory. If we map all tasks onto a single processor, our inter-processor communication drops to absolute zero. However, this result is terrible processor utilization because every other core sits completely idle. Conversely, mapping tasks to maximize our utilization often increases network communication delays. Therefore, maximizing processor utilization and minimizing communication are fundamentally conflicting design goals that we must balance. So mapping example. Okay, figure 4 represent a mapping example from A and then represent to the P2, P2, P1, P2, P3 is a processor. Okay, figure 4 shows network graph of 8 tasks from H, A through H to be mapped onto 3 physical processor P1, P2, P3. Let's look at concrete mapping problem. Suppose we have uh, okay, suppose we have 8 interdependent task label H through H. We assume that all processor run at equal speed. Each task require equal computation time, which is P seconds, and all communication path have equal delay penalties. Our engineering task is to map these 8 items across exactly 3 physical processors, P1, P2, and P3, as shown by the layout column on this slide. If we divide them unevenly, we must calculate the exact utilization period and subsequently idle period for each processor. Your job as a system architecture, whatever, is to propose a layout optimization that minimize the idle period across P1, P2, and also P3. So, mapping techniques, static versus dynamic. To execute our mapping, we classify our technique into two broad operational categories, static and dynamic. Okay, static mapping technique distribute all tasks among the processor prior to the execution of the algorithm, which is deal when workloads are predictable and uniform. Dynamic mapping techniques distribute the computational work among the available processors during the active execution of the algorithm, which is necessary when workloads are highly irregular or change unpredictably at runtime. All right. So scheme for static mapping. So static mapping, this one static mapping for data partitioning. Static mapping often rely on how arrays are distributed across memory. So block distribution. In this scheme, a d-dimensional array is split among processes such that each process receives a single contiguous block of array entries along specified dimension. For the block cyclic distribution, so this variation partition our array into many more blocks than the number of available processors, and then assign those partitions to processors in a round-robin manner. This is an excellent way to alleviate load imbalance and ideally, idling problems idlings, yeah, idling problems. Okay, idle, yeah. So what you call idling problems in irregular data set. Okay, yeah. So random block distribution. Okay, here the array is similarly partitioned in a high number of blocks, but they are uniformly and randomly distributed across the processes to achieve statistical balance. All right. And then for the scheme, for the static mapping, which is for the task partitioning, yeah. Alternatively, static mapping can be directly on task partitioning. This technique partition and abstract data task dependency graph and maps its individual nodes onto physical processes. This approach is ideal. Yeah, is ideal. Okay, this is ideal. Sorry, yeah, is ideal when the underlying computation is naturally expressible, yeah, expressible as a static task dependency graph where the sizes and computational weights of all tasks are known precisely in advance. Scheme for dynamic mapping. When workloads are unpredictable, we deploy dynamic mapping scheme. So centralized scheme and distributed scheme. Okay, in centralized scheme, yeah, in a centralized dynamic load balancing scheme, all executed tasks are maintained in common. Central data, structured managed by specialized process. Okay, this process is designated as the master, while the worker processes that depend on it to pull tasks are designated as a slave. Okay, for distribution scheme, in a distributed dynamic load balancing scheme, yeah, the executable tasks are scattered across all processes. The processes communicate and exchange tasks dynamically at runtime to balance the workload across the network fabric. Any process can send or receive work from any other process as hotspot develop. Yeah. All right. So next is a references that we're going to use. Okay, you can have this reference and also from online you got lots of that. So this is the numbers of the reference that we can use for this topic. Yeah. All right. Okay, thank you all very much for your time and attention. Thank you. Bye bye.